So I've got a new packet of notes that I'm going to hand out in just a minute. We're going to get started on doing some more trig. So we started with kind of a review of the algebraic functions. The next 3 chapters deal with more trigonometry. So we're going to do sort of trigonometry, let's not restrict ourselves to just the first quadrant, kind of seeing how that works. Do some applications of radian measure. This is all of the second chapter of notes. The exercises are in chapter 8 of the text. And then in chapter 3, we're going to do more vectors. We did a little bit of vectors in the first semester. We're going to do vectors in any quadrant this semester. And then the chapter after that is on solving oblique triangles. And I'm just giving you a heads up because it's after chapter 4. That's going to be the cutoff of material for the first test. So mostly trig stuff. Let me hand this out before I forget.
Thank you.
We have recitation at 11, and it's in room 212, so it's not in this room. 212, it's like the little room next to the electrical lab in 200. And that'll be at 11, and I'll have a practice quiz for you then. Does anybody have questions they'd like to ask on what we did last week? Okay.
What was that?
I just asked if anybody had questions on stuff we did last week.
On in-class practice?
Sure.
Could we go over number 6?
Yes.
Solve for x.
Yes. So the equation that we're given looks like this. What's the first thing we do when we solve an equation that has fractions? What?
Get rid of the fractions.
Okay, before that, before we can even do that though. Like, how do we get rid of the fractions? What? Yeah, we're going to factor the denominators because we've got to be able to identify what the LCD is, what the least common denominator is. So how does the bottom factor the first fraction?
You take it in x.
Yeah. And then we had 2x minus 5. X itself is obviously factored. What about this other denominator over here? Take out a 2. And then we've got 2x minus 5. Okay, so what is the LCD?
Two x minus 5.
Mm-hmm. And now that we know what the LCD is, we factored everything, we know what our LCD is, now we can get rid of the denominators by multiplying all terms by the LCD. Then we whip into a frenzy of canceling. So what's left with the first term? Four x. Here in the middle the x cancels, but we're left with everything else. So we have 3 times 2, or I guess 6, times 2x minus 5. And then on the other side, the 2's cancel, 2x minus 5's cancel. We just have x. Now that's a linear equation. So we could distribute. Don't forget to distribute the negative. So we have a minus 12x plus 30. And then we can combine like terms. Minus 8x plus 30 equals x. I might just go ahead and get the x's on the right side because already we only have constants on the left. So we could add 8x. And we get 30 is equal to 9x. And now it's all over but the shouting. Reducing that gives us 10/3. And then we just do a quick check and make sure that that doesn't make any of the denominators 0. But the only things that make these denominators 0 are 0 and 5/2. So we're good. Other questions? Okay. All right. Thursday's quiz, I guess I didn't write this up here, but of course we have a quiz Thursday. That'll focus on algebraic fractions and what we covered today. Okay. So let's do some trigonometry. We already know some trig, right? We did some right triangle trig, trig where we were restricting ourselves to the first quadrant, so everything was positive. We already saw that we could define the cosine and sine functions as being the coordinates of the point on the unit circle for an angle theta. So here's the unit circle is a circle of radius 1 centered at the origin. That's how we know the coordinates of these points here, right? 1, 0, 0, 1, and so on. We could see easily that cosine of 0 has to be 1 and sine of 0 has to be 0. And up here at 90 degrees, cosine has to be 0 and sine has to be 1. Of course, there's a lot of values in between. We even derived, I think, a set of values for like 60 degrees back last semester by using some algebra and geometry. But the coordinates are just give us the cosine and the sine functions. The other trig functions are derived from cosine and sine. We could see clearly from the unit circle that cosine and sine might be positive or negative, right? Everything was positive when we restricted ourselves to the first quadrant, but over in the second quadrant, we could see that cosine has to be negative and sine has to be positive. In the third quadrant, they're both negative because both those coordinates are negative. And in the fourth quadrant, cosine is positive and sine is negative. Values of the other trig functions we get just by using these basic definitions. Stuff that we've needed to know already, but here it is as a refresher. Secant and cosecant are the reciprocals of cosine and sine, respectively. Tangent is the ratio of sine to cosine. And cotan is the reciprocal of tangent. So, in this first example, we've got some angles here. We've got 30 degrees, 150 degrees, 210 degrees, and 330 degrees. We've been given the values of the coordinates, this cosine and sine, for 30 degrees. So, what we're going to do is, we don't need a calculator for this at all. What we're going to do is see how each of these other angles is related to that 30-degree angle. So this first one, in the second quadrant, that's at 150 degrees. If that's 150 degrees, can somebody tell me what the measure of this angle is? That's 30 degrees. It's 30 degrees up from the negative x-axis. So what should the coordinates of that point be right here? What should the x-coordinate be?
squared, 3 over 2.
And the y coordinate?
1 over 2.
Yeah. Okay, so we're just using the symmetry of the circle and to derive what those values are. At 210 degrees, well, that's just 30 degrees beyond the 180. What should the coordinates of this point be?
Negative square root of 3 over 2, negative 1.
Mm-hmm. And over in the fourth quadrant, 330 degrees, that's just 30 degrees down from the positive x-axis. And what should be the coordinates of that point?
3 over 2, negative 1.
Yeah. Right, so this, in the second quadrant, this is just a reflection across the x, or the y-axis. Down here, this is just a reflection across the x-axis. And the 210 degrees over in the third quadrant, you just do both, and you reflect it across the x and the y. You could also say we reflect it across the origin. It's just like 180 degrees across. Without using a calculator, what should be the sign, S-I-G-N, sign of each of these values? Sine of 320 degrees. Should that be positive or negative?
Negative.
Negative, why?
Well, that would go around, and it's 40 degrees the other way.
Yeah, so 320 degrees is going to be like
And it's
here, right?
negative.
It's in quadrant 4. It's in the fourth quadrant. So sine is negative. What about cosine of 320 degrees? Positive, because it's in the fourth quadrant and the x-coordinate is positive there. How about tangent of 320 degrees? Why?
It's the ratio of sine.
Right, so tan of 320 degrees is sine 320 degrees over cosine 320 degrees. And so that's going to be a negative over a positive. And so this is negative. So if we're confident and we're we can always tell whether or not a result should be positive or negative based on what quadrant the angle is in, we could still use our right triangle techniques to solve a lot of problems. In this example, it says find the values of the trig functions of theta if the terminal side of theta passes through the point negative 4, 3. We have done problems just like this, only they gave us a point in the first quadrant. So let's sketch this point out. Let's plot it in the plane, negative 4, 3. There it is. And so the angle theta they're talking about is this angle right here. There is no right triangle that has angle theta. Right, theta is obtuse. So what we're going to do is make a right triangle by doing our favorite thing to do in the plane, which is still just drop down a perpendicular. This is what we did in the first quadrant. It'll work just fine for us now. I'm going to use this angle here. I'm going to call it alpha. It's a reference angle. A reference angle is always like an acute angle that allows us to think of it in terms of a right triangle. So we know that the vertical leg has length 3. The horizontal leg has an absolute length of 4, but I'm going to attach the sign to it, negative 4. And then we're going to find the value r of the hypotenuse. R is always a positive length. We only attach signs to the legs, to like the things that are the xy coordinates. So if we find r, of course Pythagoras will help us out with that. So we get 3 squared plus negative 4 squared equals r squared. 9 plus 16 is 25. And we find that r is equal to 5. Now we just want to find the values of the trig functions. So the key here, the trick, is that when we find, say we find sine first, all right? So it's opposite over hypotenuse. Sine of theta. Sine of alpha, like if I treat alpha like it's a first quadrant angle, it is positive, well, I guess that would be positive. If I did cosine, you know, cosine of alpha, alpha being an acute angle, would be positive 4 over 5. But I'm using the signs here, I'm thinking about it, I'm using alpha to kind of just construct this right triangle. But I'm still attaching the signs to the legs. So when we use SOHCAHTOA, it'll actually give us sine and cosine and tangent of theta, of that angle, as long as we attach the right signs to it. So sine of theta is opposite over hypotenuse. That's still positive, as we would expect in the second quadrant, 3 over 5. Cosine is adjacent over hypotenuse. Cosine theta is negative 4 over 5, so negative 4/5. And tan TOA is opposite over adjacent, so 3 over negative 4 or negative 3/4. They said find the values of the trig function, so we actually want to get the other 3 as well. What's the reciprocal of sine? Cosecant. So cosecant theta is 5/3. Secant theta is negative 5/4. And then cotan theta is negative 4/3. Questions? Okay. Want to do some more? Okay. So now we're going to solve for an angle. We already know kind of the tool that we have solving for an angle, right? If I know what sine theta is, what allows me to find theta? Arcsine, right? So those inverse trig functions. So arcsine, arccosine, arctan, those are our friends here. Now, the book splits this topic up into 2 sections, one where they deal only with degrees and one where they deal only with radians. We're just going to talk about them both here. So when we restricted ourselves to only the first quadrant, all we needed was those functions, and we knew it would get us the only answer we were looking for. There would only be one result that we're looking for, and the arcsine and the arctan or whatever would find it for us. Now we're going to have to be a little bit careful. When you're finding the angle that you're looking for, you have to first just get everything in terms of a reference angle. So here's my first, if my angle is in the first quadrant, my angle theta is the reference angle alpha, right? If it's in the second quadrant, then here's my reference angle. A reference angle is always measured from the x-axis, never from the y. So if my reference angle is alpha, then this is the angle 180 minus alpha if I'm in degrees. So just think about going 180 degrees and then back up by alpha degrees. If I'm in radians, I just substitute instead of 180 degrees pi radians minus alpha radians. If my angle is in the third quadrant, then what I need to do is go the 180 degrees and then go alpha degrees more. So theta is 180 plus alpha. Or if I'm in radians, pi plus alpha. If my angle is in the fourth quadrant, I'm going to figure out what that reference angle is, alpha, and then I'm going to say, oh, I'll just go the full 360 and back up by alpha degrees. Or 2 pi radians, back up by alpha radians. So we're always going to get everything in terms of that angle first. We have a really good reason for this. This is a fail-safe way of finding all the angles you need. the arc functions are designed specific to give specific kinds of answers. So arc sine will only give you an angle in the first or fourth quadrant. If the angle you want is in the second or third quadrant, arc sine will never give you that angle. And in fact, even when it gives you a fourth quadrant angle, it'll give you an angle that's between 0 and negative 90. It'll treat it like a going backwards angle. Same with arctan. Arctan will spit out angles over here. Arc cosine will spit out angles in the first and second quadrant only. So, so between 0 and 180 or between 0 and pi radians, it will never give you an angle here. So if I start out by saying, I know maybe what quadrants I'm looking for, and I can certainly figure out what's going on in the first quadrant, I know exactly, like, they all agree in the first quadrant. Like, if I know that sine is positive, or cosine or tangent is positive, and I use arctan or arc cosine or arc sine, it'll always give me that first quadrant angle, without fail. That's perfect. Then I just need to know how to make the adjustments to find the angle that I want in my quadrant. Here's the other thing. Let's say I know that sine of theta is equal to a half, okay? And I choose to use my calculator to find arc sine of a half. It'll give me one answer, 30 degrees. But we can tell by looking at the circle, there are two places where sine is going to be equal to a half because it's got to happen over there too. So I still need to be able to make an adjustment to find both the angles that I'm looking for. There are almost, unless you're at one of the extreme values, there's always going to be two angles that you're looking for if you know the value of a trig function. So let's do some practice. And you'll note this says find theta for theta between 0 and 360. They're saying find everywhere on the circle, for one go around the circle, where sine theta is positive 0.6374. So, okay, our reference angle is alpha, a first quadrant angle. And no matter if this were a positive or a negative 0.6374, sine of alpha is always a positive. Same for cosine or tangent. Like when you're finding that reference angle, whatever the value of the trig function, just take it and make sure it's positive, because it's a first quadrant angle. Everything's positive in the first quadrant. Now I know how to find alpha. This is where we're going to use the arcsine function. So alpha is arcsine of 0.6374. I know I want an angle in degrees because they said where theta is between 0 degrees and 360 degrees, so they were pretty explicit about that. My calculator's in degree mode, so second sine, to pull up the inverse function, 0.6374. And I get 39.6 degrees. Okay, so there's my reference angle. Now I'm going to find the angles I want. If sine theta is a positive 0.6374, and it is, all I'm doing is looking to see whether the value of sine they gave me is positive or negative. In what quadrants is sine positive? 1 and 2. Okay, so let's find the angles we want. Here's our quadrant 1 angle. Theta is just equal to alpha, so 39.6 degrees. In quadrant 2, what I want in quadrant 2 is, whoops, that's quadrant 3. I want to take 180 degrees and back up by alpha degrees. So I'm going to take 180 minus 39.6 degrees. (140.4). So these are our two angles. And you could check. If I pop in sine of 140.4, 0.6374, and a little bit. I need to approximate the angle, so that makes sense. How's that? Okay. When I'm doing a problem like this, I almost always, see how like I sketched out a little mini like plane there to like kind of identify where I'm looking? I almost always start that way. So here secant is negative 7.704. What function is secant related to? Cosine. So what is cosine theta? Yeah. So there's cosine theta. Cosine's negative. So what quadrants am I looking at here? Where's cosine negative? 2 and 3? Okay. So when I find alpha, I'm going to do 180 minus alpha and then 180 plus alpha. All right. So cosine theta is a negative 1 over 7.704. Cosine alpha is positive 1 over 7.704. And then we'll take arc cosine of that value. So 82.5 degrees. Now, let's find the angles we want. We said quadrants 2 and 3. So theta is 180 minus 82.5. And that's 97.5. And what do we do to get the angle in quadrant 3? Yeah. $262.5. How's that? We can check, right? How do I check these answers? Yeah, right? So like 1 over, negative 1 over 7.704. I'll just find that approximation. Is negative 0.1298. So if I plug in cosine of 97.5, I get negative 0.1305. That's a little bit far off. Maybe I shouldn't have. Oh, you know what? I have a better way to check. I kind of approximated a bunch there. I'm going to do 1 over cosine of 97.5. And there's negative 7.661. Why am I feel like we're off. Negative 7.704. $82.5. Maybe I shouldn't have approximated so much. I'm going to try this. And this will be, what, 4.6? And this will be 4.6 or 5.4. Let's try that. Oh, that's much better. 0.1298. Okay. maybe just a note about rounding. Questions? Okay. All right. This one's kind of similar. Find theta, where theta is between 0 and 360 degrees, where cosine is equal to 0.870. And then they give us this extra information, and sine of theta is -0. We know that sine is negative. What does that added piece of information do for us? Yeah, right, so there's 2 quadrants where cosine is positive. There would be quadrants 1 and 4 on the right side. But if we also know that sine is negative, where does that put us? Yeah. So we only need one angle this time. We know that cosine of alpha is a positive 0.870. And so alpha is arc cosine of 0.870. That'll give us some angle. $29.54. Maybe I'll go a little further this time. So our angle we know is in the 4th quadrant. Alpha is always measured from the x-axis, so there's our alpha. How do we get theta? Minus 29.54. So we get 330.46. How's that? Good. Let's do another. This looks kind of just like the ones we were doing. What's different about it? We're in radians. How do you know? Yeah, where theta is between 0 and 2 pi. So we're definitely in radians here. So I'm just gonna switch my calculator to radian mode now. They tell us that cosecant is a negative 1.133. What quadrants is that in? And how do we know? Mm-hmm. Yeah, so if sine is negative, 3 and 4. Yeah. It's in the bottom quadrants. So when we find alpha, we're going to go alpha degrees down from the 180, alpha degrees down from the 360. Or radians. Down from the pi radian and down from the 2 pi radian. So sine theta is negative 1 over 1.133, which means sine alpha, it's positive 1 over 1.133. Alpha is going to be arc sine 1 over 1.133. $1.081 Radians, I know we talked about this a little bit last semester, but with radians, you can write RAD if you want. It's customary and conventional to leave units off, so you're going to see that a lot in the book. If they say theta equals 1.081 and there's no degree symbol or any units attached to it, we need to understand that means it's in radians. It's okay to leave units off. Some people like to write RAD just for their own purposes to remind themselves what they're measuring their angles in. So we have our reference angle. Let's find the angles we want. So in quadrant 3, theta is pi plus 1.081. Definitely can't do that in my head. 4.223. And then quadrant 4, we're going to take 2 pi minus 1.081. .202. How's that? Not too bad. Okay, well then, let's do another one. Again, this one's in radians. We could tell because theta is between 0 and 2 pi. They tell us a tangent is negative 1.830. So where is this angle? Where are we looking at? Say that again. 2 and 4. Yeah, so tangent is positive where sine and cosine are either both positive or both negative. And it's going to be negative where one is positive and one's negative. So when your x and y coordinates have different signs, that's in quadrants 2 and 4. So we know that we're looking to find our reference angle and then make the appropriate adjustments to find this quadrants 2 and 4 angles. So tan of alpha, we set up a new equation. Tan of alpha is a positive 1.830. We're finding that first quadrant angle first. So alpha is arctan of 1.830. And that's 1.071. So in quadrant 2, how do we find theta? What? Pi minus alpha. So pi minus 1.071. .071. And in quadrant 4, how do we get theta? Mm-hmm. And 5.212. Questions? You're going to want to make sure that you're aware of what mode your calculator's in, because we're kind of switching back and forth now more than we did in the last semester. So that's kind of a gremlin that comes to haunt people sometimes. So one thing I'll just, when you're finding angles, first of all, I put a little sticker at the top of my calculators that just remind me to check my mode. Of course, I'm used to seeing it so much that sometimes I don't notice it. But one thing I always do notice, if you get, when you're using the inverse, this comes up more. This is easier to notice if you're using the inverse trig functions. So inverse trig functions spit out an angle. When I get big-ish numbers, I know I'm definitely in degree mode. Big-ish numbers meaning more than 7, 7 or higher. In fact, I'm going to say if it's 4 or higher, that you could only be in degree mode. If something's in radian mode, it's either going to spit out an angle in the top half, if it's arc cosine, between 0 and pi, so between 0 and 3.14, blah, 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 blah. Or if arc sine and arc tan, it's going to be between negative pi over 2 and pi over 2, which is like 1.7 something and negative 1.7 something. So you get these really small numbers when you're in radian mode. So when I get something really small, I think, oh, I might be in radian mode. And if I get something bigger than 4, I know I have to be in degree mode. So sometimes if I just get a really small number, I kind of check. I know it's possible that I'm in radian mode. And of course, it's possible to have a really small angle in degrees, right? Like something that's 1.2 degrees is tiny. But okay. Are we ready to do more? Yeah? Are you sure? Okay. So, speaking of radians and how much we love them, let's just remember, I'm going to do something up here in the margins first, that a radian gets its name because we're comparing something to a radius of a circle, and a radian is defined by length. By something very natural to measure, length. An angle, it's easy for us to kind of visualize measuring an angle, but like if you take an angle, it could cut out an arc that's either small if you're really close to the angle or big. Think about concentric circles and think about cutting out the same angle, and it'll measure out different lengths on the bigger circles versus smaller circles. When you define what a radian is, there's 2 ways to think about it. They both are tied to length. If I have a circle of radius 1, okay, so I'm fixing that radius at 1, then whatever this angle is that I cut out, that is equal to the length in radians, equal to the length that it cuts out, the length of the arc that it cuts out on the circle. So if it's a radius is 1. If I go halfway around the circle, that'll cut out about 3.14, whatever your units are. If I don't fix the length, or if I don't fix the radius, so the radius could be anything, we'll call it r, then if I cut out 1 radian, if I measure an angle of 1 radian, then that's the same thing as cutting out an arc length equal to the radius. Or another way to think of that is you have a fixed radius r, right? We'll take whatever that length is, measure it up the circle to cut out an arc. That will define 1 radian. So a radius and radian, they have the same kind of root word. A radian is tied to length, innately tied to length, which is why when we're doing a lot of applications that involve measuring lengths or other things that we can get from length, like area or linear velocity, like think about a wheel spinning around and how fast a point on the tip might be moving and how that's related to the angle, like revolutions per minute, right? That kind of angular velocity. We always want to make sure that we're measuring our angles in radians. Radians are tied to this measure of length. Degrees are tied to nothing other than the fact 360 is a really convenient number. It's divisible by lots of things. So the applications that we're going to look at require us to be using radians. The formulas that we're using are only valid if our angle is measured in radians. Incidentally, the mode that our calculator is in isn't going to matter because we actually don't need to use the trig functions to do any of these applications. So our first application is on arc length. So if I measure, if I've got a circle here of radius r and I measure out an angle theta in radians, then this arc length, which we'll call s, because the angle could be anything, right? So I'm not fixing it at 1 radian or anything. So measure out any arc length you want, then or any angle that you want. The arc length that it cuts out will just be that angle in radians times the radius. Like the radius is like a scalar, basically. So if I want the length of the arc here, our angle they gave us is pi/6 radians. The radius is 3 inches. So I'm just going to start. S is equal to r theta. R is 3 inches times pi/6 radians. Now, you could write in radians if you want, but what you need to understand is that radians are dimensionless, which maybe helps explain a little bit more about why we just leave the unit off when we're writing out an angle in radians. And measuring an angle is like there's no dimension there, right? Because it could be a big arc length, could be a little arc length, depending on how close you are to the center. So I'm saying all this to point out that when I multiply 3 inches by pi/6 radians, since radians have no dimension at all, the units are just inches. And it makes sense that an arc length should just be a linear measure, right? So this is, what's 3 times pi/6 is pi/2 inches. If you want, you can approximate. It doesn't matter what mode your calculator's in here because we're not using the trig functions, right? Just pi divided by 2. Whether I'm in degree mode or radian mode, pi/2 is still about 1.57 inches. And I bet I'm going to go ahead and just approximate these results because in most of these they're application problems, and so usually to kind of give context we often round them instead of leaving them in terms of pi. You want to do another one? Okay. So, a nautical mile is defined to be the length of arc along a great circle of the Earth for a central angle of 1 minute. So now we have to, what are minutes? Jacob knows. You're really excited. Does anybody remember how we define a minute?
60 seconds.
What?
60 seconds.
60 seconds, but also?
A 60th of
Yeah, there's 60 minutes to a degree. 60 seconds to a minute, 60 minutes to a degree. So, and does anybody know, you might not have heard this term before, but does anybody know what a great circle of a sphere is? So if you take a sphere, I wish I had one here. If you take a sphere,
cross-section of any.
not just any cross-section. Like I could draw a little circle on a sphere anywhere. Like I could, like if I had, let me try this.
Like it's a cross-section of the radius.
Yeah, like, so here's a sphere, right? I could draw any kinds of circles. I could draw a little one that goes like around here, right? I could draw a little circle that's right here. A great circle has to go around us like circumference, like around the widest part,
It's like the maximum.
like an equator. Like the equator is a great circle, but it doesn't have to be the equator. It could be anything as long as it goes through the center, right? So, so that's what a great circle is. And a nautical mile has been found to be 1,852 meters. And we want to know what's the measure of the Earth's radius. So they're telling us an arc length, right? The nautical mile is a length of arc along a blah, 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 blah. Okay, and it is 1,852 meters. So that's S. That's an arc length. We know that we're going to use S equals R theta, and we want to find R, right? I mean, we could do some algebra here. We know that if S is equal to R theta, what's R equal to? What is it? Close. What?
That's the.
No.
It's estimated.
S divided by theta. Right? Let's just write a little bit of algebra here. I know it's earlier than we're used to doing math, but we can do it. Okay, so I know what S is. So this is going to be 1,000 852 meters over something. What we over the angle. They gave us the angle. The angle's 1 minute. Do I just divide by 1 minute? Jacob is shaking his head. No. No, not no.
Do it until you
What do we need to be true about our angle, theta? Has to be in radians. We actually have to convert 1 minute to radians. So let's do this up here. So we know how to get to degrees, yeah, 60 minutes to a degree, so 60 minutes to 1 degree. And then how do I get from degrees to radians? Sorta. I think that's involved, but what's the equivalence? Yeah, why pi, like what's the equivalence? Why isn't it 180 over pi? Nope. Pi radians is equal to 180 degrees. So I'm putting the 180 goes on the bottom because I need to cancel out the degrees, and then there's pi radians on top. Okay, so I'm going to leave this in terms of pi. 60 times 180 is 10,800. So pi over 10,800 radians. That's our theta. And that's going to go down here. So I'm dividing by a fraction, so we'll just rewrite it so we can multiply. So 1,852 times 10,800 divided by pi. $6,366,707. What are the units here? Meters. Now, in a problem like this, if you looked up the answer in the back, you know, they'd probably be thinking, oh, okay, well, 1,852 meters is a measurement. I'm going to treat it as approximate. There's 4 significant digits. So I'll write this as 6,366,000 meters. You could do either. Like, it doesn't matter to me. Or if we could also round it or convert it to kilometers. So 6.3. Oh, that would be 367, not 366. We round, don't truncate. Kilometers. Not bad. Oh. 6,000. There we go.
So according to Google and conversions, we're enough for miles. I converted meters to miles, and then if the radius here, then give
Oh.
it miles.
Oh, okay. Guess maybe that's only a little bit considering
Well,
how
it's
big.
because the Earth's not a perfect sphere.
It's all, yeah, it's not
It's
a, I mean, we're using the term radius. I guess how do they measure the radius of the Earth?
By the equator, which is where it alters. It's the
Right.
part.
And it's what? It's got to be the sea level part, I would imagine.
I think so.
Yeah.
I guess the most even part, which
Well, it's also a nautical mile, so I'm thinking we must be, yeah. Okay, so we did some stuff with the arc line. The next application is on area of a sector. Oh, wait, before we do that, I'm going to go back here for a second. What's the circumference of a circle? Does anybody remember what that is? How we find the circumference? What?
2 pi times radius.
It's, yeah, 2 pi r, right? So the circumference is 2 pi r. There's a formula we know and love. So with the circumference, what's the measure of the central angle? If I'm cutting out an arc and I want it to be the whole circle, what's the angle? What? We're only in radians here.
2 pi.
2 pi. So the circumference formula is just a special case of the arc length formula. The area, so if let's do the same thing. We start with a circle. We cut out, we measure an angle from the center. There's our central angle, theta, radians. Instead of measuring the arc this time, I want to measure the area of the sector that it cuts out. And we can find that by taking theta r squared over 2. And if I wanted the area of a whole circle, what would the measure of that angle have to be if I wanted the whole circle? What would the angle be? The whole circle, we just answered this question. 2 pi radians. If I want this to go all the way around, so I get the whole circle, then the angle is 2 pi radians. So if I use this formula with an angle of 2 pi, this reduces to pi r squared, which is, of course, the area of a whole circle. So the area of a circle is just a special case of this formula for area of a sector. We're going to do some examples. Again, you got to be in radians for any of this to work. So in the very first example, they give us the radius of 5.25 inches and a central angle of 218 degrees, but we're too smart to fall for that. We know before we plug anything into this formula, we're going to convert that angle to radians. Again, what's the equivalence? How do I get from, what's the equivalence between radians and degrees? So you're giving me the multiplying factor, and I'm asking what's the equivalence? What's equal to what? So many radians is equal to so many degrees. Yeah. And the reason I'm asking it in that way is because it's not always clear which one has to go on top. So I want to make sure we understand that these are equal, and that's how I know that 180 goes on the bottom and the radians go on top. So 218 times pi divided by 180 and that's 3.805 radians. So the formula is theta r squared over 2. So this is 3.805 times 5.25 squared, 25 inches squared, over 2. What are the units that we're going to use? Yeah, yep, square inches. We could see exactly where it comes from. The radians are dimensionless, so I even left them off. Some people choose to write in RAD, and that's fine, but just understand they are dimensionless. They add nothing to the units in your final answer. So 3.805 times 5.25 squared divided by 2 gives us 52.44 square inches. Questions on that example? Okay. Whoops. Next one, we're going to find the angle. They gave us the radius, they gave us the area. We want to find the angle theta. So we start with the formula A equals theta r squared over 2. We could plug stuff in first and solve. I kind of am a fan of doing a little bit of algebra in the beginning. If we isolate theta, then we have something that we're just ready to plug the values into. So we want to solve for theta, which isn't too hard. We could multiply both sides by 2 and divide by r squared. So theta is 2a divided by r squared. Now we have everything we need to plug in. 2 times 75.5 square feet divided by r squared is 12.2 feet squared. So we'll throw this stuff in the calculator. Divided by 12.2 squared. I get 1.015. What are the units on this? What? It's radians. Yeah. So there are no. Notice that square feet cancel with square feet. So there are no like linear dimensions that come with us. It's in radians. Partly because yes, it's dimensionless. We could tell. Also, the formula is only valid if theta's in radians. So I know it couldn't possibly be in degrees. Degrees are dimensionless too, I guess, for that matter. But the flip side to you have to have your you have to have your angle in radians to make the formulas work when you're plugging your angle in. The flip side of that is if you're solving for an angle, it is automatically in radians, and we need to keep that in mind. Let's do some more. Jacob Vance wants to do a lot more. Yeah. Okay, so we did arc length, we did area. Now we're going to talk about angular velocity. So imagine like a wheel spinning around, like a bicycle wheel or something. So how fast it's moving, how fast it's spinning around. We think of rotational motion in terms of angles. I think of how many RPMs, it's like revolutions per minute, just how many times does it spin around each minute. That's an angular velocity. When we're using angular velocity in our formulas, we're going to need to make sure that those are in radians per unit time and not revolutions or degrees. But if you have, like think about, again, concentric circles. So imagine I've got an angle that's, this is spinning around, right? And this wheel moves from this point to that point in like 1 second, all right? A point on the tip of the inner circle only has to go through this smaller distance over that same time than a point on the tip of the bigger circle. So the point on the tip of the bigger circle has to move faster, more, inches or centimeters per second or whatever, to spin that through the same angle than the smaller one. And this is sort of the idea behind the formula, that linear velocity on the tip is sort of proportional to the radius, right? How far away you are from the center, and that linear or that angular velocity is a theta per unit time, right? An angle per unit time. And we usually denote this by omega, like a little scripty omega, kind of looks like a W. But that's your angular velocity, so that's in radians per time. And v is the linear velocity. So that's like a length, an actual length, in particular, an arc length per unit time. So v has units like centimeters per second or feet per second or kilometers per minute or something like that. And omega has units like radians per second or radians per minute. And they're related by this formula. V is equal to omega r. So you get the linear velocity just by taking that angular velocity. And the radius is a scalar. Right? So multiply it by whatever the radius is. The bigger the radius, the faster you're moving around. And that makes sense to us. Let's do a problem. An example: a person on a hang glider moving in a horizontal circular arc of radius 90 meters. The angular velocity is 0.125 radians per second. Find the linear velocity v. So they told us the radius is 90 meters. They even told us the angular velocity, and it's even in the correct units, radians per second. So that means we're all ready to use our formula, V equals omega r. So 0.125 radians per second times 90 meters. 0.125 times 90 is 11.25. What are the units?
Meters.
Meters per second, yeah. So the radians are dimensionless. We lose those, but we end up with meters per second. Let's try another one. Satellite maintains an altitude 22,320 miles above a fixed point on the equator. And they tell us the radius of the Earth is 3,960 miles. What's the linear velocity of the satellite? So what's important to note here is that it maintains this altitude above a fixed point on the equator. So if you think about whatever the angular velocity is of the Earth as it rotates on its axis, that's going to be the same as the angular velocity of the satellite, because it's, what do they call it? Geosynchronous. It's above the same point. So here's like the Earth. Here's its radius, and this guy is above the surface of the Earth. There's our satellite. So this distance from this Earth's surface is 22,320 miles. This radius of the Earth is 3,960 miles. R will be both of those combined, because the circles that we're talking about both have a center of whatever the center of the Earth is. So the little r that we're going to use is their sum. Twenty-two, 320 plus 3,960, 26,280. 26,280 miles. And we want to know the linear velocity of the satellite. So we have the radius. Great. V equals omega r. We know it goes in for the radius. What about omega? How fast does the Earth rotate on its axis?
That's every 24 hours.
Yeah, a full revolution every 24 hours. So we know what omega is in revolutions per hour. How many radians in a revolution? 2 pi. And so we can reduce, we get pi over 12 radians per hour. So now we know what to plug in for both of these. Pi over 12 times, radians per hour, times 26,280 miles. And now we'll throw this in the calculator. You get 6,880.09. What are the units? Miles per hour. It's a linear velocity. So when we had to think about what that angular velocity was, just to do a little deducing based on what we know about the Earth, and we understood that meant it was one full revolution. Sometimes they'll give you a problem where they give you omega in revolutions per whatever unit time, like RPMs. And I just want to point out that when they do that, revolutions is abbreviated with a lowercase r. So sometimes people see like r per minute and they think that they're being given omega in radians over time. But if they mean to write out radians explicitly, they'll either write RAD as an abbreviation or write out the words radians completely. So if you ever see R per minute or R per hour or whatever, that's always revolutions. In this last example, let's see, the flywheel of a steam engine is 0.3 meters in diameter, and it's revolving at 420 revolutions per minute. How fast is a point on the rim moving? So let's see. First of all, they gave us the diameter. What do we have to do with that? Yeah, so we need the radius, so that's going to be 0.15 meters. And then they gave us omega in revolutions per minute. So we need to get that in radians per minute. So 420 revolutions per minute. And sometimes I'll even just write out REV. Like I'm just going to remind myself that's revolutions and not radians. Whatever you got to do to kind of remind yourself of that, go ahead and do it. One revolution is how many radians? 2 pi. So the revolutions cancel. 2 pi times 420 is 840 pi radians per minute. And now we're ready. V equals omega r gives us 840 pi radians per minute times 0.15 meters. Throw this in the calculator. $395.84. What would be the units here? Meters per minute. There we are. Look, 1 minute to spare. I love it when a plan comes together. So the quiz on Thursday, we'll probably have a couple questions on, algebraic fraction stuff, a couple questions on this stuff. Check Canvas, because I have to update the thing that I gave you. I wasn't planning ahead when I wrote that. That's still a good practice, but there's going to be more problems to look at. Let me know if you have questions. Definitely, I can promise you there will be at least one question where you're told that, tangent or sine or secant, whatever, takes on some value, and tell me all the angles that produce that. Like solve for an angle, but maybe we'll have to find them in a couple different quadrants. And maybe one of these application problems and one or two fraction problems. There'll be a practice quiz and recitation in about 20 minutes, so, feel free to come to that. I'll post it to Canvas also if you don't make it.